Hi friends, let us continue from where we stopped. And previously we have seen how voltage is induced from a single loop with the help of Faraday's law of principle. So on this single loop, if we realize we have a commutator segment called, a split ring commutator. What is the purpose of this split ring commutator? What is the purpose of this? So, according to Fleming's right-hand rule, what we have seen previously, the direction of the induced current change whenever the direction of the motion of the conductor changes. It means, now, if you see this diagram, we have one loop connected in between north and the south, and there is a commutator segment. F is connected to AB segment and E is connected to CD segment. Now, an armature, let's assume the armature is rotating clockwise and the conductor at the left is moving towards. So when the armature complete half cycle, it means 180 degree, obviously this coil side is going to be shifted. Now CD segment is going to be under north and AB segment is going to be under south. And if you see the direction of the current, it was moving from A to B in this case. Now it is moving from B to A in this case. But the segment is still the same, F. F is going to connect to this. So, when the armature complete half rotation, the direction of the motion of that particular conductor will be reversed to downside. Will be reversed to downside, sorry. Now, because in this case it was under north side, now it becoming south, obviously the direction will going to be changed according to Fleming's right-hand rule. Hence, the direction of the current is going to be altering. It means that in this case it was this side, if it was plus, now it is going to be this side, it becomes minus. But if you see the position of this commutator segment is not changing, because here AB segment is connected to F and AB segment is connected to F. So with a split ring commutator, the connection of the armature conductor also get reversed when the current get reversed. Means when current reversal is occurred, commutator segment reversal is also occurred. It is occurred. And therefore we get the same direction of flow of current. We call unidirectional current will be found on the terminal XY, or through the load. Now see, in this case current was flowing like this. Now similarly the current is flowing in the same direction through the load. Why? Because this segment is going to be changed with the coil side. Therefore, to get unidirectional current in external circuit load, a split ring commutator arrangement is done. That is the purpose of the split commutator. See, due to this, the signal, it is supposed to be sine wave, plus this side minus this side. But with the help of this split ring commutator, the direction is going to be unidirectional, one directional only. This happens unidirection. So if you see this signal, it is called pulsating DC. DC with a large number of impurities. So how to become DC? Because we are talking about DC generator, we are supposed to get a DC signal at the output. So in order to get DC, this impurity has to be reduced. How we can reduce this impurity? This signal is produced by one loop. If I add one more loop, say this, black and the white one, I have two loop with four commutator, split ring commutator. So the signal is going to be pulsating DC still, but with less impurities. So if I add a number of coils here, if I make it 3, 4, 5, 6, the impurity is going to be reduced and it becomes almost a smooth DC is coming. That's how the DC is generated from a DC generator. Having said this, let us go to the internally induced voltage. Of course, this is what we have seen in our last time class, but a little bit we have to get in depth to the real our generators. So, like we said previously, in order to get induced voltage, three things are required. You remember the equations. You remember the equation. So from the equation, as you may remember, induced voltage, now what we are saying, generated voltage in the case of our generator is going to be BILV sine theta. And these are the 3 or 4 parameters that determine the amount of voltage generated. So, induced voltage, BVIL we say. And the voltage out of the armature of a real DC machine is equal to the number of conductor per current path times the voltage on each conductor. It means now having this in our mind, E induced is going to be BIV, the maximum induced voltage. But in our real DC generator, this is for a single loop. So I'm going to have Z number of conductors. I'm going to have Z number of conductor, Z BILV with respect to paths. This is what it's saying. It means the voltage of our armature of real machine is going to be number of conductor per path. For each conductor, there are different paths are there that we may see some other time. This path, it depends on the this path depends on the armature connections. It depends on the armature connection. Therefore, induced voltage going to be Z, where Z is number of conductor in our armature, and A is paths, number of paths for current flow. Therefore, induced voltage, or I can say generated voltage, is going to be Z by A BIL V maximum, and the voltage of our armature on the real DC machine is going to be ZVBL by A, where Z is total number of conductor and A is the number of current passes. And what is V? Velocity. The velocity of our moving conductor. And the velocity can be defined. The velocity can be defined as in our machine, V can be R omega. So what is our radius of our rotor? Therefore, we can replace this with the expression what we have mentioned it now. It means now our generated voltage EG, it is going to be now Z A B L R W omega. So now from our background knowledge, if there are peoples or our machine, the portion of the real associated with each pole, the portion of the area associated with each pole is the total area divided by the number of poles. Which means that if you have people on the machine, the portion of the area associated with each pole is going to be area divided by pole, obviously. Area divided by pole. And what is our area? Our DC generator, since it is a cylindrical, the area is going to be 2 pi RL by P. 2 pi RL by P. And we need also some other fundamental thing. The total flux per pole in a machine, is going to be flux density times area covered by single pole. And the flux, now the flux phi is going to be flux density times area of pole. And this area of a pole again, we say that it is 2 pi RL by P. RL by P. This is L, length of the conductor. P. This is a flux. This is a flux. Therefore, we can present the previous or this example with another expression. What is the expression? Let me have new space. The expression EG, don't forget this, it is Z by A, it is Z by A, B, L, R, omega. Right? And we have also said that phi is going to be, what we say? It is B 2 pi RL by P. Like this. Right? Now, let me express this in another term. This expression can be expressed in another way. EG can be expressed as ZP 2 pi A 2 pi A and 2 pi RLB divided by P times omega. See, I'm trying to express this equation in another form. What makes sense? If I cancel this with this, P with P, what is remaining? Z by A and RLB omega. If I cancel this expression means if I cancel this 2 pi, this expression is going to be the same as this one. So I'm trying to express it in another form, nothing new here. So EG can be this one. What is remaining now? If I cancel this with this, the remaining is this one. But what this term means now, P 2 pi A times. What this term means? What this term means? This term means it is phi. This term means this one. So this is going to be phi, and omega is remaining outside. So what is finally what we are remaining with? e.g. we are remaining with ZP 2 pi A phi omega. So I can represent this with K phi omega, where K is going to be ZP by 2 pi A. What is this? This is internally generated voltage for any DC machine, K phi omega, internally generated voltage. So, EA or EG we usually call it in generator, and EA in motor, back EMF it means. So it is going to be K phi omega, K phi omega. What does the equation tell us? It tells us the induced voltage from our generator in terms of K machine constant, in terms of the flux, in terms of the angular velocity omega in rad per second. And Z means machine constant. I said it tells you the number of conductors, the pole, and current passes inside the machine. That's why we call it a machine constant. But in modern industries, it is common to express the machine revolution per minute instead of rad per second. So we're in a position to convert rad per second into revolution per minute. So the conversion from revolution per minute to rad per second can be used by using this formula. We can use it. Now, if we replace this in the previous equation, in this equation, if we replace this with, let me show you here. So we said EG is going to be K phi omega. So K phi. Now this revolution per minute can be converted into rad per second by the help of this one, 2 pi n by 60. 2 pi n by 60. Now, what was that? ZP by 2 pi A times phi 2 pi n by 60. Right? Let me cancel this phi. Now what is remaining? ZP by 60 A times phi times n. Then EG, generated voltage, or EA, is going to be Z pi P 60 N phi N. We can call Z K pi N prime. Now K prime is going to be ZP 60 N. Don't confuse with K. K is ZP by 2 pi A. The previous K is ZP by 2 pi A. Now K prime is ZP by 60 N. So, having said that, we can proceed to the EMF equation. Of course, what we have seen is the EMF equation for DC generator. Therefore, just to summarize it, the internal generated voltage for our DC generator is going to be K phi. This is in terms of machine constant, Pz. That is what we have seen previously. Same as this one. Okay? This one. ZPN, or in rad per second, this one. So, for a simple lab winding, there are simplex and the duplex lab windings are there, what we call lab and wave winding. Our armature winding has got two ways of wounding on the shaft of our rotor. One is a lap winding and the other is a wave winding. We'll come to this later on in detail. Anyhow, in a lamp winding, the number of parallel paths is equal to the number of poles. A is equal to P. If that is the case, the generated voltage is A is going to be P. So E generated or generated voltage is going to be P phi N Z divided by 60P. And P the number of poles, is a flux, is a rad per second revolution speed, and this is a conductor, and this is pole. So if you cancel this, so this is going to be phi N Z by 60. But if the winding of our armature is wave winding, simplex wave winding, P is always 2. P is always 2. So we can represent this P by 2, then the equation is remaining same, this one. So P Z N, I mean P phi N Z by 120. The difference is the winding on the machine. Having said, we can go to the example. We can go to the example. So on this example, we are going to elaborate points what we have seen till now. The first example says that the DC generator has 8 poles and 120 slots with 8 conductors in each slot. If the flux per pole is this much, 0.04 wave, determines the EMF generated when the speed is 600 RPM, it says. When the speed is 600 RPM. So then under this, how we are going to attempt it now? What are the givens? What are the givens? And the givens are P is given 8 pole, and slot of our machine is given 120 degrees. Slot is a place where we are going to place our windings, and conductors is given in each slot. 8 conductors are there, and the flux per pole, it is 0.08 Weber, the unit for flux. And we already told that it is a lap winding. In lap winding, A is always equal to P, we said. How much? 8 degrees. And the conductor is supposed to rotate at 600 RPM. I think this is what is given. So what is requested? EMF generated voltage. So it is asking what is the generated voltage. It says what is the generated voltage. So we know that generated voltage is going to be ZP phi N by 16A. We know this. But what is it? Total number of conductors in our DC machine. What do we know? We know the slot, place where we are putting the wind. We know in each slot 8 conductors is there. Therefore, number of conductors on our machine is going to be number of slot times number of conductors in our slot. Therefore, Z is going to be 120 times 8. It's going to be how much? 960 conductors are there in my machine. Now I came to know Z. P is already there, flux is there, N is already given, A is already, I know it, it is equal to P, then directly plug and get the values. Plug. So, EG is going to be now Z, what do we say? Z phi N P 16A. Now my Z is 690. No. My Z, sorry. My Z. Z is going to be 960 times. My phi is 0.04 times. N is 600 times P is 8 divided by 60 times 8. So generated voltage is going to be 384 volts. That's the way we are supposed to attempt. So EG is going to be 384. And on the B, it says what should be the speed of the rotation if the induced voltage is to be 500 volt? Assumes armature connection is lap winding. Now, on the B, what is requested now? Say that now the induced voltage is EG, 5 volt. 500 volt is supposed to be induced. So what is the speed? It says. It's simple. What we are going to do? Just from the previous equation, EG ZP phi n by 16a. From this, if you try to solve for n, EG 16a divided by ZP phi. Everything is given. What is changing now? EG is given. How much it is? 500. This is a new value. And 60 times A is already lap winding. A is equal to P. It's a lap winding. And P is 8. Z is already, we know, 965. 0.4. Then plug it in the solvent. Then you will get the result. And you can check by yourself. N is going to be 781.25 RPM. You can check it by yourself. Thank you very much for listening to me. We will continue next time. Thank you.